Hi folks, thanks for joining me in this session. So I'm going to talk about hybrid memory compression technique and especially focused on AI. So of course when we say AI that automatically means HBM memory. So this is actually work that was done by our research team, Angelos, who is our CTO. And then this was done in collaboration with Chalmers University out of Sweden. So just some quick background, Zero Point Technologies is an IP licensing company and we focus on hardware accelerators for memory and storage compression. And then also on-chip compression. But what I'm going to present in this session actually is some advanced research work we've been doing actually to address the challenge of memory shortage for AI workloads. By the way, feel free to stop me in the middle if you have any questions. Don't wait till the end. If you think of some question, just stop me. So the number one problem, and by the way, this is data from Google and semi-analysis. They looked at how much power does it take to do a chat GPT query versus just doing a Google search, right? So if you look at the chart down below, it's almost 10x. So this itself is actually an unsustainable growth. If you think of, if AI truly does ramp up the way the industry analysts are predicting, then this is a pretty big challenge in terms of the power. And the other interesting thing is, of course, a lot of the focus is actually on inferencing. So we hear about training and all these huge clusters that the hyperscalers are putting up with tens of thousands of GPUs. That is typically focused on training. But for inference, you need typically a totally different infrastructure. So right now, everyone is in the just build it mode, right? Everyone has a blank check to build the biggest clusters. But at some point, you have to recover the money. You have to get some return on the investment. So that's when things like power and efficiency start to matter. The other thing, we're talking about GPUs, right? GPUs are prevalent right now. But one of the key things about these GPUs, definitely if you look at the chart on the right, let's start with the chart on the left. The teraflops are definitely increasing gen over gen if you just look at the NVIDIA GPUs. And the power is going down, but again, at some point it's starting to flatten out. And one of the key things with these AI workloads is the inference, right? If you remember the previous slide, we said inference is almost 85% of the workloads that is projected over the next few years. So that is actually, the arithmetic intensity for inference is very low compared to training. So which means this becomes a memory bound problem. So now that's why the challenge of you need some way to grow the memory faster. So this is an interesting chart. If you look at the chart on the left-hand side, what this is showing on the y-axis is years, so out to 2030, and on the x-axis, and on the y-axis, this is the full SoC bandwidth, right? The peak bandwidth. So if you look at the two zones, and by the way, this is data presented by Dimitrios Ziakis from Intel. So he presented this at a JEDEC forum, and the key insight that he was showing is you have these two clear zones where you have kind of the low, I'll call it the lower performance type of application, and then you have high performance applications. So, but the interesting thing is that the HBM growth is starting to flatten out, which means, I didn't mean to go back. Let me go back one slide. And actually that is reflected in the wafer starts. Right? If you look at the wafer starts, if you look at this chart out here, the HBM is the orange color on the top. So if you think about the AI boom, then the wafer starts for HBM should also be reflected in the growth. But the reality is there's still a lot of other technologies like DDR, LPDDR, GDDR, which are still going in accounting for the wafer starts. So definitely some other technique is required in order to increase the total capacity of memory, right? Especially HBM. So what is that technology, right? Right now, that's kind of the ask from some of the companies like Intel and some of the other hyperscalers are saying, oh, we need some other breakthrough to help memory scale faster to keep up with the demands. So So one of the ways that people are trying to address this problem is through hybrid memory systems. Right? When we say hybrid, what we mean is you use HBM as your near memory, so near compute memory, and then you use DRAM as a far memory. So of course there are some trade-offs. HBM is high bandwidth, of course, as we know, but then with DRAM you can get a large capacity, but then the performance may not be as great. So this is one way that you can achieve a better system performance by developing a hybrid solution. And the chart out here, or the picture out here, kind of shows your typical system where you have a processor with multi-level cache hierarchy, and you might have like a last level cache controller and HBM controller, and maybe also a DRAM controller. So you can turn this into a hybrid system theoretically. Now, the problem with this is, you can use the near memory in cache mode. What that means is you actually don't use HBM capacity, you just use it as a cache for the far memory, but now you're not using the actual near memory. The other way you can use it as a flat mode, which means you take the HBM memory and then you take the far memory, both of them together. But now you have to do some swapping of pages in and out. And this actually leads to increased traffic from, say, HBM to DDR. And actually then it cuts into your efficiency. Now, a third method you could use is actually a hybrid mode, which means you take a portion of the HBM or near memory as a cache, and then use the rest of the HBM as regular HBM memory. But again, out here, what you're doing is you're reducing your effective capacity of HBM. So there are lots of challenges. You can do these interesting things. So then the question we asked, because being a company that develops compression IP, we said, can compression in near memory in HBM actually help solve the problem? And then what are the challenges? Of course, there are always some challenges. So we believe our solution, and we have a whole paper that we've published on this, there's a link to it, is this HMComp technology, which can compress data in the near memory and then use that to actually create a cache space for bandwidth intensive DRAM pages. So that's kind of our solution. It's kind of like a hybrid, but with some intelligent mechanisms that we have developed. And one of the mechanisms is an intelligent metadata layout. So typically when you're doing things like compression or you're moving pages from here to there, you're changing the address space, you need to have some metadata to let the processor know what's going on. So we've come up with a novel way to reduce the overhead of the metadata. And I'll show you some of the results, but what we see from the simulations is actually with this technique, you can achieve a speed up, right, IPC, instructions per second, a speed up of about 24% and reduce the swap traffic, which by up to 60%. And by the way, if you remember the earlier slides, I was talking about this challenge, right, the power challenge. So every time you're moving data around, right, you're burning power. So that's why we believe by reducing the swap traffic by 60%, that can significantly help even the power problem, not just the capacity problem, but also the power problem. So we looked at a couple of architectures, and we looked at a baseline architecture, we'll call it BL1, which is flat mode, where pages are interleaved with congruent groups. So what's a congruent group, right? So if you have one page which is in HBM, and then you might have, let's say, 5 pages which are stored in DDR. but they all map to the same page location in HBM when you do the swap in, swap out. So we call that a congruence group. The second baseline where we'll be comparing the results to is actually swap bandwidth demand or bandwidth demanding pages that require extremely high bandwidth or frequently being called in paging in and out. So we use that as another technique. And then we also played around with the granularity of the blocks, like what you move around and you compress. So depending on whether it's a 4 KB block or it's a sub, or like a 4 KB page, or it's a sub page, or it's a block of the lowest one we can do is 64 bytes. So these are some of the parameters that we were comparing our architecture against. So I spoke about the congruence group, but this is just a visual showing if you have page A in HBM and the rest of the pages B, C, etc., they are sitting in DRAM. But they all, when they need to be swapped into the processor, they all would need to be swapped into the location of page A, and page A would need to be swapped out. So that's a group, a congruent group of pages. So the design that we came up with, right, is actually a mechanism where we employ the swapping, but we do it intelligently. What we do is we use compression. We compress the data in HBM, or we compress certain blocks in the near memory HBM, and then whatever space is freed up, we actually use that as a cache. So I showed you before, if you use HBM as a cache, you lose some capacity. But if we compress some of the data and then use that extra space as cache, now we have a dual benefit. We still have a cache, but we haven't reduced the effective capacity of HBM. So that's kind of how we, the basic architecture of HMComp. And the trick is, can you do this efficiently, right? And if you look at some of the things that we add in, the block in gray is what we add into your classic design. So if you look at a memory controller today, it's going to look like this, right? It would just be a separate HBM controller, DRAM controller. And with our architecture, what we would do is we would add in this HMComp block, which would do a couple of things. One is it would do compression, decompression on the fly, and then it would also have a cache for the metadata. And then we would actually hold the metadata table in DRAM. So if you look at this little gray area out here, we would hold metadata in that space. So that's another unique part of the design is if you put metadata in HBM, that can waste a lot of space. Depending on the granularity of your block or your pages. But with this technique, we actually don't waste the space. We just use the metadata cache in the HBM. So it becomes pretty effective way to store the metadata. The other innovation that we came up is, I think the previous speaker was talking about DRAM and efficient ways of managing power. So all of these DRAM memories, they have ECC, error correcting bits, and many of them are actually redundant or can be used for other purposes. So one of the techniques that we employed in this design is use some of the unused ECC bits to store block level metadata. So now this again, we are not actually using the usable HBM space, we actually use the ECC bits to save some of this metadata. And we came up with an efficient encoding mechanism within 6 bits that helps us locate the right block. Whether it's, if you look at this diagram, it's a little complicated, but what this is trying to show is 2 things. Assume you have these different blocks, right, which are stored, but let's say you have a page A in HBM and this page B is in DDR. So we can dynamically detect what pages can be compressed, and then we bring them together, and then we swap the blocks out. So we do this intelligently. We monitor the bandwidth, we monitor the compressibility of blocks, and then intelligently do the swapping, which lets us be efficient and not waste a lot of overhead. Now, so theoretically, this was the architecture that we came up with. So we said, okay, how do we verify that this will actually perform? So we start off with a simulator. So of course, Gem 5, as many of you may be using, we use Gem 5 as a baseline simulator, and then we use some parameters. It was a classic cache design with L1, L2, last level cache design. And then we actually included a compressor algorithm. Now, note that in this architecture, the compression algorithm actually does not matter. It could be whatever compression algorithm. We have our own proprietary algorithms, but for this purpose, we use CPAC, which is a well-known compression algorithm in the literature. And then, of course, we had some parameters for near memory and far memory. So we were able to set all of this up in a Gem 5 simulator. And this is what, the way we did it is we took the baseline methodology, which is just a flat memory model space, and then a swap-only memory model, which is the techniques that are used in, typically used. And we compared all the results to those methods. And then the benchmark we used was actually a Spec 2017. We used that with a pretty small footprint. So the interesting results we saw is, if you look at this chart, there's many pretty colors out here. But the HMComp, that's this architecture I'm talking about, that's the last bar out here in blue. So one of the things you'll observe is on the x-axis is a bunch of the benchmarks, right? Part of the spec suite. There's the different types of benchmarks. So we ran those different benchmarks, and on average, we observed a 24% IPC speed up by using this architecture. Right, so there were some cases where the performance was on par, or in like one or two cases, the performance was low. But on average, we observed a speed up of about 24%. The other thing I was talking about is the swap traffic, right? Whenever you move pages, it burns power. So what we're looking at out here is we looked at the impact of swap traffic due to HMComp. Now, out here the HMComp, which is the new technique, the new architecture, is in yellow. So of course, lower is better, right? You want less swap traffic. So on average, we were able to cut down the swap traffic by about 41%, and it peaked at about 60% in some of these benchmarks. And the other thing I told you is the metadata, the performance is sensitive to the metadata. So we did some sensitivity analysis to see how would the different metadata perform. And of course, there is a sweet spot, which is the 256 KB metadata cache seem to be kind of the sweet spot for performance. So there is some tuning that is required. So with that, I'd like to summarize this HMComp architecture. It offers, we observe speed up of about 24% and reduce the swap traffic up to 60%, which is significant when you look at the amount of power that is being burnt in these AI chat GPT style systems. And this technique of compressing data in the near memory and then freeing up some cache space, that became an effective way to not reduce the HBM effective capacity. And then that actually allows us to expose the entire memory space, HBM plus the DDR, as one big space to the accelerator. And finally, the way we developed our metadata layout, that helped us to get even higher efficiency because we're not wasting the HBM memory to store metadata. We're only storing the metadata cache into the HBM. Okay, so the question was, do we have a benchmark for more AI testing? So if you look at some of these benchmarks that we played with, these are more spec benchmarks. But actually, we'd love to work with you too if there are some specific, maybe like MLPerf, I don't know what you might have in mind. I'd love to chat with you offline. If there are some benchmarks we could collaborate on and test those out as well, for sure. But for now, while we publish these results, we had only tested with the spec 2017 suite of benchmarks. It's just for LLM using. Yeah, that's a good point. Yeah, we haven't specifically looked at for LLM, but yeah, we'd love to chat offline if there are some well-known benchmarks we should test this with. Let me see. So, and by the way, that's part of the call to action, which is this is OCP, right? So the open compute. So that's why we want this to be an open collaboration as well. So in fact, if there are ideas like, hey, let's test with these LLM benchmarks, and then that leads to some kind of a use case that we want to prototype, right? So what we did was we built this whole thing in simulation, but this can easily be converted, well, not easily, but it can be converted into an RTL or FPGA style prototype, and then we can actually run some of these benchmarks. So one of the challenge with Gem 5 simulators is they're pretty slow to run, right? So they take a long time because you're simulating this whole thing. So trying to run an LLM would be pretty challenging. Even these spec benchmarks which we ran, to keep it in a reasonable amount of time, we only ran it for a few days or whatever. So, but yeah, definitely love to collaborate, and that's what OCP is all about, is the collaboration. So love to work with some of you to build a prototype, verify these results, maybe run some interesting use cases like LLMs. And then maybe there is a chiplet to be built, right? Because if there is enough interest and the problem is big enough in terms of the memory, bandwidth, capacity, and power, then maybe we can discuss maybe collaborating on building a chiplet or a chip together. And then what we would need to do in this case, for example, you mentioned LLM. So it would be good to know what is the metric we are trying to achieve. Then we can, as a OCP community, we can actually collectively agree on a target spec, and then measure the results against that. So that is exactly what we would want to achieve. So let me stop here for any questions or maybe open discussion or ideas. If you have some ideas or better ways to do it or some critique, would appreciate it. Yeah, please.
Is there any overhead or compressing?
Yeah, so the question is there any overhead for compression and decompression? Answer is yes. So the overhead is in two aspects. One is, of course, to implement the compression, decompression circuit, we have to add some area, right? So, and this area depends on the exact algorithm that you pick. So some of the IP that we have today, which has gone into RTL, we've tested with TSMC 5 nanometer technology, Samsung process. It can be as small as 0.1 millimeter square, but it can also go up all the way to 1 millimeter square before some of the other algorithms which are more dictionary intensive. So it really depends, so we can trade off. But for cache line compression, so that's one of the proprietary algorithms that Zero Point has developed. For that, the IP itself is very small, closer to the 0.1 millimeter square. Performance. So the question is, what is the performance overhead? So compression, decompression, what we observe typically takes, with our proprietary algorithm, anywhere from 5 to 7 cycles. So to give you an example, if you're clocking your processor at 1 gigahertz, that means 5 to 7 nanosecond latency. So yes, there is some overhead, but so that latency was also modeled in some of these performance estimates. So you can plug in different latency numbers for the compression algorithm and see how your performance would be impacted if you were to choose a different algorithm. Yeah. Other questions, comments, ideas?